Now that we've talked about cylinders, we're going to talk about some more interesting, more fun to deal with shapes, specifically quadric surfaces. A quadric surface is the graph in space of a second degree equation, which is in three variables, x, y, and z. So second degree, all of the terms are maximum squared. So we can have x squareds, y squareds, z squareds, and then we can have pluses and minuses. So this takes you back to, you learned in your trig class a little bit about the graphs of conics, hyperbolas, ellipses, circles, and parabolas in two space. We're going to kind of expand on that, and now we're dealing with these equations in three space. We're going to have a lot of standard formulas which look really similar. So what we're going to talk about now is, how we can tell them apart from just looking at them. So we're going to talk about the characteristics, and we're going to identify 6 basic quadric surfaces. And these are, they'll include ellipsoids, paraboloids, elliptical cones, and hyperboloids. A sphere is an example of an ellipsoid. A sphere is a specific ellipsoid where we have the same dimensions extending out in x, y, and z. But if you made one of those a little bit longer in one direction, that would give us a different shape. So let's talk about the standard form for a quadric surface first. So let me write our kind of standard form, or the most general and brief equation of a second degree in three variables. So what would that look like? We've got ax squared plus by squared plus cz squared plus dxy plus exz plus, you guessed it, fyz plus gz plus hy plus iz, oh, I thought I could fit it, plus j equals 0. So I'm going to pause and rewrite that nicer. So here's our formula. All these coefficients, a through j, represent constant values, right? So they're constant coefficients. And this equation leads to these 6 quadric surfaces we're going to talk about here in a second. In general, the formulas we're going to talk about, they're going to be centered about the origin and in what we would call, like standard form, no shifts or translations. But for example, these values, gz, hy, and iz, they're going to lead to translations and shifting to the left and right, as well as shifting something up or down. And you guessed it, we're probably going to use some completing the square in here to help us determine, what that equation is. So, this formula, I'm not going to require you to remember this, but recognizing the pattern and being able to put it into a standard form, which is what we're going to do. It's pretty similar to stuff that you've already done in your trig classes when you were dealing with your conic sections. So let's work on an example before we consider those 6 general shapes. So an example of something we might see, which is going to be far less variables in it, than that standard form up above. We have z equals x squared plus y squared. So, let's think about this and break down how we can graph it and develop what it is. So one thing we want to notice is this z value. This z is always going to be positive. Z is always going to be some number greater than or equal to 0, because this is always positive plus another positive number. Z is always going to be positive. We can plug and chug, make a table of values, and plot tons of points in 3 space, but that's not effective. So what we're going to do is we're going to find some traces, and we're going to choose values for one variable. So for example, I might choose values for z. So say we let z equal 0. what does that give us? So plugging 0 into that given equation, I've got 0 equals x squared plus y squared. So that's a circle of radius 0, which is really just a dot at the origin. All right, let's choose z equals 1. That's 1 equals x squared plus y squared. So at z equals 1, we have a circle in the xy plane of radius 1. And because I see this kind of circle pattern, you know, I can obviously choose z equals 2 and z equals 3, but I'm going to choose z equals 4. 4 equals x squared plus y squared. So that gives us a circle of radius 2. So remember, these circles are in the xy plane, and as we move up along the z-axis or around the z-axis, these circles are going to come or begin having increasingly larger radii. So that's the idea. We think about, you know, what we can identify, and what these trace shapes are. So we're going to be having lots of circles, almost concentric, if you will, but they are expanding out. So what does that look like in R3? So we're noticing if we let z equal some constant, some number, that's always providing us with a circle. And again, those circles are of increasing radii. How about if I let x equal a number? If x equals a number, we would have a constant. And if this x squared became a constant, we would have y squared equals to z. So that's a parabola in the yz plane. So we've got a parabola in yz. That circle is in xy. And similarly, if I let y equal some number, let y equal a number, this becomes a constant, and I have x squared equals z. So this is a parabola in the xz plane. So our shape is going to include parabolas and circles. So if we think about graphing that in R3, so my x's go back, my y's go back, my z's go down. Of course, we know that z is always going to be positive, so this is all going to be above the x and y axes. So graphing this, we said we would start with a dot at the origin. And if we let z equal 1, which would be right there, 1, I'm going to go ahead and count up to 4. So we're on our z-axis. There's y and x. So if we let z equal 1, we're going to get a circle in that xy plane. That's a circle of radius 1. So I'm going to kind of draw that around there. And if we look at z being equal to 4, up at the 4th rung on that vertical ladder, we're going to have a circle of radius 2, so a bigger circle. And so we can see that, you know, it's going out, it's expanding up. If we consider what's going on in the YZ plane, because that's what we're looking at head on. So we said the YZ plane, we'd be getting a parabola of sorts. So essentially what this shape is, it's a elliptical paraboloid. Even though those shapes are circles, we call them ellipses. So it's this, you know, parabolic shaped bowl with a circular top, because a circle is really just a specific type of an ellipse. So we've talked about this one shape. We have 6 general shapes, and we're going to examine those in the following video.